So, good evening. I'm Calvin Paul Joseph, and today I'm going to conduct the week 3 problem solving and doubt clearing session for the course Control and Tuning Methods in Switch Mode Power Converters. So, the outline of today would be I'll be discussing about a practical voltage source. We'll be discussing what are the objectives in switch mode power converters control. Like what do we need to consider? What is our main objectives? What are the things we have to look out for, etc. Then I will discuss about feed forward control in switch mode power converters, followed by feedback control, which can either be single loop, that is voltage mode control, or multi-loop, which one good example of that is current mode control. And then we will solve some questions and followed by MATLAB demonstrations. Okay. So let us start with a practical voltage source. And what do you think is like a practical voltage source? So we'll start with week 3. So we have what is known as a practical voltage source. Ideally, this is our voltage source, that is say VDC. Okay. Irrespective of how much current is being drawn by the circuit, it would the voltage over here at its terminals would always be VDC. This is an ideal voltage source. But in a practical case, what happens is there's resistance, there's parasitic inductance, there's parasitic capacitance, and they might be distributed, etc. But what do is we lump them. So when we lump them, we represent it as follows. This is your VDC. There's like parasitic resistance, parasitic inductance is there. There's your parasitic capacitance and some ESR of the capacitor. This is your LF, this is your RL. And this is your terminal voltage. Okay. So this is your terminal voltage. So what you can, this terminal voltage is not equal to VDC when there's some current. When this current is greater than 0 or current is not equal to 0. So there will be a voltage drop. There will be some oscillatory behavior that depends on the current being drawn. Okay, so this is the practical voltage source. And what happens is when there's a practical voltage source, there will be what is known as some distortion. There will be some distortion VT due to the current drawn. And this distortion which is there, like that will affect the converter which is connected. So you guys might have like kind of seen this example. Let us say we switch on what you say some motor, some large motor or some large electric load in our house. Sometimes what will happen is the lights which are there, it will dim for some short period of time. Why is that? Is because when you're turning on a motor or when you're turning on some electrical appliance, there is no back EMF there. Okay, so lots of huge inrush current is being drawn. When that huge inrush current is being drawn, then the voltage, like when the current is very high, when this current is very high, this voltage will go down. And when this voltage goes down, the tube light or other things will go dim. Okay, the fan speed will reduce, fan might even stop. All these will happen. Okay, so that is like a practical thing which we see. So what we observe is like when there's a dip in your voltage, supply voltage, due to some big load being connected, your light is getting dim. Okay, light is getting dim, tube light is getting dim, etc. So that can happen, that happens, but the tube light is not much of an issue. The tube light is not much of an issue because we can manage. But in your practical system, where you have this is connected to your processor, you have some processor, some mobile processor or some processor, and in between there will be you will have your converter, your which mode power converter. So this voltage, this is supplying your processor. This output voltage is supplying your processor. So when there are these fluctuations in your VT, that also will get reflected in your output voltage. And that fluctuation will affect the load which is connected. That is your microprocessor, microcontroller, or whatever load is connected. Okay, and that is not desirable. So what we want, one thing is we want to have a good or clean voltage source. As much as possible, we can do that. So many times what happens is you use these large wires. When you use a large wire from here to here, in a wire, what will be there? There will be some inductance, there will be some resistance, etc. So you'll have to reduce that amount of that. Okay, you'll have to reduce that. Further, sometimes what they do is in PCBs and all, they will connect lots of input capacitors. There will be these lots of input capacitors. What this input capacitor will do is it will kind of cancel out this inductance, this parasitic inductance which is coming up, as well as it will take off all the ripple current so that the current which is drawn over here is, like constant. It is less, it is free from the ripple. So these are some advanced concepts, but these are used in PCBs. Okay, in PCBs, when you will design, probably you have also designed, but these are there. Okay. So next is we'll consider what are the objectives of switch mode power converter. Why do we use switch mode power converters? So you have heard about the buck converter, right? You have heard about the boost converter. So buck converter is required when you want to step down the voltage. Boost converter is needed when you want to step up the voltage. So that means you have your input voltage over here. You have this is your DC-DC converter, and this is your load. And the objective is if you have some voltage, you'll have some voltage. And this load will draw some current, I output. Okay. Most converters, what you want to do is you want to fix this. This voltage should be fixed. So, like when I started learning about power electronics in my BTech and various times, like I used to wonder why do they design something just for some fixed voltage? For some fixed voltage, why can't it be adjustable, etc.? Okay, there are some cases where it needs to be adjustable, but in most practical cases, your voltage which you want, it will be fixed. It will be regulated. So mostly you want your output voltage to be regulated. Okay, regulation means you have some fixed value, say 5 volt, 3.3 volt, 1 volt. You want to maintain that voltage fixed. So that is your one objective. So what happens? Like this is what you want to do, but why it doesn't happen? Like you would have seen, right? There are some cases you can have what is known as a disturbance. Okay, you will have a disturbance. Like let us say this current can change. This current being drawn can change. The current can go high, it can go medium, it can go low, it can go high. Many things can happen. Okay, your load current can change. This input voltage also can go high, or it passively solve a practical voltage source. It can also have some fluctuations can be there, right? So what we want is this output voltage, this voltage over here should be fixed. It should be fixed. It should be constant. It should be regulated. It will not always be regulated. It might have a dip. Like let us say, it may dip a little, but it should not dip too much. Okay, there could be a slight increase, but it should not be too much. That depends on your specific application. So as per your application, you will design it accordingly, and you will make sure that it is within the acceptable range so that your load will not get affected. So like recently, like what you say, you have your, let us say your keyboard or various electronic instruments. Let us say you have a public address system where we use lots of amplifiers, etc. The new amplifiers, the new digital electronic equipment which you have, they are very sensitive equipment. That is, you need to always have what is known as a stabilizer. Probably many of you would know. You need to have a stabilizer. So you have your input AC supply is coming. You will have a stabilizer which will give you a stabilized voltage, and then you can connect all these electronic equipment. So as these equipments are the newer equipments, which are recent equipments which come, they are very sensitive and they need to have the stabilized voltage. And why it's happening is because we have these stabilizers, we have these converters which can give you all these stabilized regulated voltages. Okay. So this is there. So these are the objectives. Like these are some of the objectives of these converters, that you want to maintain regulated output voltage. There are various disturbances like your load current can change, input voltage can change. There are various parasitics also inside your converter. There's a lot of measurement noise also will be there. So in spite of all these problems, all these non-idealities, we have to find a way through control where we will practically make sure that my output voltage will be regulated, it will be fixed. Okay, so that's the objective of control in switch mode power converters, and that is what you'll be learning in this course a lot. Okay, you'll be learning a lot of it. Okay, so if there are any doubts, Leah, you can ask, or I'll proceed with the next part. Okay, so next is you have various feed forward control techniques. Okay, various feed forward control techniques are there. So let us consider a buck converter. You have in a buck converter, this is your input voltage is there. Okay, that is followed by this switches. Then you have an LC filter, CL. Then you have your load. Your load can be a resistor, it can be some another converter, it could be some constant current load, LED load, many things are there. So this is your main switch Q, this is your Q bar switch. And you want this output voltage to be fixed. This output voltage, it has to be fixed. Okay. So what we know, ideally what do we know? Your V output is equal to D into V in, where D is the duty of your switch Q. That is your switch Q is going like this, etc. This is the time period T. This is the duration dt. So your V output is equal to D into Vn. Okay. Now, what happens is, this is in ideal condition, but what happens is that you have these on resistance over here. You have another on resistance of this switch. You have the inductance DCR is there. You have the capacitor ESR is there. Also, these switches have a turn on, turn off. They have dead time. They have reverse recovery charge. These switches also, they have certain capacitors also they have some parallel capacitors also they have a body diode also they have. So all these things result in the output voltage will not be equal to D into Vn. So in that case, what should be done? What is done is, you will, let me first start with feedback control and then I will talk about feed forward control so that it will start with basic thing. What you do is, you will measure V output. You will measure this V output and you will have some reference value. Say you want your V output to be 5 volt. Okay, you want your V output to be 5 volt. So let me go to the next page. Hope this is visible. Okay. Sure. What you will have is, you will have a reference value. This is your reference value. That is, you want it to be 5 volt. You will compare it with your output voltage. What is the output voltage now? What is the output voltage which is present now? That when it is not equal to that, there will be some error will be there. This is known as your error will be there. There, you will pass it through some controller. This is your controller. Your controller will generate some duty. Some duty signal it will generate that will go to your converter. And your converter in turn will generate some output voltage, which comes over here. Okay. So if your V output is required 5 volt, okay. Your V in you is 12 volt, or let us make it simple. Your V in is 10 volt. Okay, that means the duty required is 0.5. The duty, theoretically speaking, required is zero point 0.5. But what happens is when you give this duty of zero point 0.5, output voltage will come, let us say 19 volt. Sorry, not 19 volt. It would come, let us say 4.5 volt or something. It is less. So what happens is output voltage is less. You compare it with reference, you get some error. That error passes through a controller. That is, you can have a proportional, integral, derivative. They can be for the type 2, type 3, various other controllers are there. That will generate some control command. Based on that control command, you will generate one particular duty. Based on that duty, you will apply the gate signal, and that will generate your output voltage. So the objective of your controller is it will make sure that this error is zero. Its objective is to make sure the error is zero. So if what happens is your input voltage, if it fluctuates, your output voltage also will fluctuate a little. But your controller should respond in such a way that the fluctuations in output voltage is cancelled out. Is cancelled out fast. Cancelled out quickly. Okay. So this is your feedback control. Feedback control means, like, suppose let us consider teaching. Like I'm teaching now to you. Now, if you tell me, sir, that this your voice is not audible, or this part which you taught is not clear, you are giving me feedback. When you give me feedback, I should listen to it, and based on that listening, there's some error. I realize there's some error, then I should pass it through some controller. Means I should process it, and then I will change how I'm giving my input. Perhaps then I may change. I may have to connect some headphones. Okay, I may have to switch off my fan, or many other things are there. Okay, so that is how we practically do it. Practically, we do it in human life. Similarly, over here also in the control system and in the switch mode power converter, we have our feedback. Okay, feedback is there to do. Now there are two types of control is there. Two basic types which are taught by sir. One is your voltage mode control. Voltage mode control. That is short form is VMC. So in voltage mode control, what happens is it's the same. We have this reference. You compare it with your output voltage. You generate an error. It passes through your controller. Your controller will generate some command that is your vcon. Okay, you generate a vcon that is compared with your RAM. You have one RAM. Okay, this is your sawtooth RAM. So when your vcon, when your RAM becomes more than your vcon, you get a reset signal. Reset signal that goes to your R, and you get a set pulse every time period. That is your set pulse. This generates your Q, your gate signal, which goes to your converter, and that in turn generates your output voltage, which in turn comes here. So this is your mechanism for voltage mode control. Any doubts in this? You can ask doubts if you have. Okay, so this is for voltage mode control, and it is like a single loop. It is a single loop control, right? Because we only have this loop. We only have this loop is there. So this is our single loop control. Next, we have what is known as current mode control, which is known as CMC. Again, we have this reference. This reference should be there. It has to be there. Because we are regulating the output voltage, so we need to know. This again generates your error. This again passes to your controller. Your controller generates your IREF. Okay, generate your IREF. Okay, this is not minus plus. This is uh, your comparator, sorry. Hmm. When your vcon is less than this. Okay, when your vcon is less than the RAM. So now you have your IREF. So instead of this RAM, what do we do is we use the inductor current actually. Because your inductor current, it rises, falls, rises, falls. So it is also like a RAM. So we use that information. We use that inductor current information. So we have to sense the inductor current. So we sense IL. That will again generate my reset. And I have a set which is periodically being applied. That generates my Q, which goes to my converter. And that generates my IL as well as it generates my V out. So now if you will observe, this is one loop. This is another loop. So you have an inner current loop and you also have an outer voltage loop. So you have two loops. You have an inner current loop, which is supposed to be much faster, and you have a slower outer voltage loop. So you have two loops are present. So that's why this is two loop control. It's also known as cascaded control or master slave control. There are some various terms for it, but basically it is current mode control. Hmm. So any doubts or queries still here? Okay. So through this control, which we will see, sir has also shown various simulations, etc. Sir has shown, and I hope you guys have understood it. I hope you have seen the lectures and everything. So there are various control techniques are there. Now voltage mode control as an issue is voltage mode control VMC is affected a lot by VN. When there are disturbances in VN, the output voltage, when it is controlled by VMC, there are a lot of fluctuations. But in case of current mode control, it is not as sensitive to input voltage fluctuations as voltage mode control. Because current mode control has, like the inductor current is dependent on your input voltage. So if your input voltage changes, your inductor current shape also changes. And that change in shape of the inductor current is kind of like helps you to reject that disturbance in your input voltage. So that's an advantage of current mode control. Secondly, current mode control also makes your inductor behave like a constant current source, kind of. So when it does that, the dynamics of your inductor disappears, kind of disappears. And only you have your outer voltage dynamics. So that becomes much easier to control, much easier to design a controller for that. But in case of voltage mode control, you have your L and your C and everything. So it becomes a little bit advanced. It becomes a bit more complicated. It becomes more, parameter dependent. When L changes, C changes, everything becomes more parameter dependent. Whereas your current mode control, because of that inherent current feedback which it has, it becomes a little bit more robust and a little bit more easier to design the controller. Okay, so that's the advantage of current mode control. But current mode control is affected a lot by changes in your load current. When your output load current changes, current mode control takes time. It takes time to react to that. Why? Because it has a slower output voltage loop. It takes the feedback of the output voltage, compares it with your reference. You get the error, then you get a reference. So it takes time to react to that. Similarly, your inductor current will not change instantaneously. It will also take time to respond to the change in the load current. That is why current mode control is not it is quite dependent on your load current. It gets affected a lot by your load current, right? So for to overcome these challenges for voltage mode control, what is done in some cases is you use V in feed forward. You use input voltage feed forward. That is, your input voltage has some disturbances. You use that information, you pass it to the controller, and that helps it to reject those disturbances. Similarly, if you can sense your load current or if you can estimate your load current, you can use that in your current mode control, and you can use output current feed forward. Okay, that is also possible. Okay, it can be done. Any questions till now? Okay, I'll proceed further. Okay. Okay, so let's start with the questions. Like I made a lot of questions and I don't know how much time it'll take, but let's see. So this is a practical voltage source which sir has drawn. Hmm? So I want you to tell me what is the DC impedance of this practical voltage source. What do you think is the answer? What is the impedance of this practical voltage source? DC impedance. Okay, Arun is saying RF. What about others? We have many people. We have Anushree, we have Divya, we have Sudhanya. Okay. You can also give your answers. See, if you're feeling shy, you don't want to unmute, it's also fine. You can send a message. But it would be good if you could give actual real-time feedback. Hmm. Okay. Yeah, Anushree, I don't understand what is RGIT. Okay, it's RF. RF. Right, it's RF. Okay. So this is like easy. What you should understand is in DC, your inductor is shorted, your capacitor is open circuit. So capacitor is open circuit, no current can flow through the RC as well. So your impedance of the practical voltage source, the input impedance, or no, sorry, the output impedance of the practical voltage source is just your RF. This is your voltage. So when your current will increase, this VT will reduce dependent on your RF. So then what is the function of LF and CF? Will your LF and CF affect the performance of the voltage source, or it won't affect? What do you think? I mean to say, do LF and CF also have an impact in the performance, or it is fine? Yeah. So what happens is LF and CF are energy storage elements. They store energy. Now, when you have a transient, what happens? You're going from one state to another state. So it is these LF and CF also have to respond to that. They have their oscillatory behavior, their oscillatory dynamics, all that come into the picture, and they have an effect. So as much as possible, you must reduce LF and CF. Okay. Next question. Feed forward control. These are some statements. Can you tell me which is correct? Okay, one is feed forward control improves the disturbance rejection in switch mode power converters, which we saw, like I explained, right? Voltage mode control is affected a lot by input voltage disturbance, whereas current mode control is not that much affected. Let me say. So what do? They have something known as input voltage feed forward. So how do you generate your duty in voltage mode control. You have your some Vcon when that is less than your VRAM, and your ramp is increasing like this, it is going like this, right? That is your reset signal, that is your set signal, which is coming periodically like this, and this generates your Q. Okay. So what do they do in this case is, this has some maximum value, V max, right? And effectively your duty which is generated is your Vcon by V max. Okay, and it will have some slope. That slope is actually V max upon T. But we consider that starting from 0. This is the slope M. Now what is done is, they change that slope depending on the input voltage. That is what they do is, they make the V max is equal to some original slope K into Vn into T. This is how they make their V max. So your V max becomes proportional to V in. Okay, it becomes proportional to V in. Now, your duty, you know how what it is. It is V output by V in. So your V output is what? D into V in. So your V output, your D is what? V con upon V max into V in. So your V output is what? V con is there as it is. E max is K into V in into T into V in. So your V in and V in gets cancelled. So it becomes kind of like V con upon K into T. That means your output voltage in this case, it is becoming independent of V in. Okay? That is how you are kind of rejecting. So whenever there's a change in input voltage, it is kind of reflected in the duty, also gets adjusted accordingly. So that is known as input voltage feed forward. And this is also used a lot. This also is used in power factor correction circuits, where we want to maintain the inductor current in phase with the input voltage so that we can get unity power factor. So there also they have to use input voltage sensing they use. They also have a method in which they will kind of divide that input voltage by the square RMS value of the input voltage, such that that loop gain which they get is independent of the input voltage. So that is also there. It's a very standard technique which has been there for many years. Okay, that's an advanced bit of control, that is for AC to DC converters. But we are currently focusing on DC to DC converters. And so this technique is there. So this is known as input voltage feed forward. It has application in case of buck converters. In boost and buck boost converter, it's a bit difficult to implement because the expression becomes non-linear. It is not completely dependent. It's not completely rejecting your input voltage, etc. Okay. So through feed forward control, you can minimize the effect of that disturbance. But if you will see these things which I've told you, these things which I've said, they are very idealistic. They are not true. They are not completely true. Because what is my assumption is, like, my assumption is D equal to V output by Vn. But this is not true. It is not true because it is dependent when the load will change, the drop will change, the output voltage will not be fixed. It is dependent on the load current, right? This is a very idealistic expression. Okay. So input voltage feed forward, in an ideal sense, it helps. It actually helps. It is giving you some information prior. Like suppose you know what questions will come in your exam. Some basic idea that these topics is very important. These topics only you prepare and go. From these topics only the answer questions will come. Then you have an advantage, right? So it's kind of like feed forward gives you that sort of advantage. But anyway, you have to prepare. Anyway, you have to derive everything and go. You have to be confident in all that, right? And you should not make silly mistakes or blunders, right? That is there. So feed forward gives you a kind of advantage. It gives you that extra information, which gives you kind of edge, which improves you. Okay. So that is thing of feed forward control. But feed forward control in this explanation which I've derived, and in other cases also, it is very idealistic. It is not always practically, it will not completely eliminate, it will not practically give you the complete accurate regulation. Okay, that is why over here it's asked, sorry. Feed forward control, it requires additional sensors. It is true, you need to sense your input voltage, you need to sense your load current, or you need to estimate it. Okay, so it becomes a bit more complicated. Okay, the parasitic and unmodeled dynamics can be overcome by using feed forward control. Feed forward control cannot eliminate the effect of parasitics. Like parasitics is there. Like I said, you have this resistance drop, right? You have this, you have this, you have all this. See, feed forward considers that these all are not there. It neglects it. That's how you get V output is equal to D into V in for feed forward. But it is not true. Like all these unmodeled things, all these parasitics are there. And so these are a limitation. So because of those actual practical realistic things, feed forward cannot give you the complete solution. Feed forward is not the complete solution. So what is the best way is you need to have feed forward, but also you need to have this kind of this feedback. You need to have this feedback. That is, you can take some corrective action that, okay, through feed forward is saying that I must give duty 0.5 and I will get my output voltage to be 5 volt. But when I actually do that, it is not happening. My voltage is only 4.5 volt. So what happens is through feedback control, you realize that you have to increase your duty a little bit more. Maybe you have to give duty 0.54. And when you give duty 0.54, your output voltage comes out to be 5 volt. So feedback plus feed forward is the best solution. It's like one of the best solutions. Okay. So that's how feed forward is good, but it needs feedback to actually regulate it perfectly, not perfectly, very well, in a good sense. Okay. So that's why this is false. Parasitic and unmodeled dynamics can be overcome by using feed forward control. No. Feed forward control neglects that. Feed forward control requires additional sensors and complex processing. This is true. You need additional sensors, etc. Feed forward control improves the disturbance rejection in SMPC. Yes, because you're getting some extra information. It helps you to do that. But feed forward control has become relevant due to recent technological advances in digital processes. No, feed forward control has been there for many years. It is there in ICs. It is there in PFC circuit, which I mentioned earlier. Right, so it's been there. It can be done with analog control as well. Okay, so are there any doubts regarding feed forward control, or can I proceed to the next question? Okay. So next is input voltage feed forward in the buck converter. Okay. Yeah, so that's what I explained just now. Okay, let us solve this. So we are targeting question 3. So what do I have? Input voltage 12 volt, output voltage 4 volt. They are saying switching frequency is 500 kilohertz, output power is 20 watt. Okay. Switching frequency is 500 kilohertz. Output power is 500 watt. 500 watt? 20 watt. Okay, it is 20 watt. Now, they are saying we are using voltage mode control. And they are saying we have to use, okay, VRAMP is 1 volt. Okay. So, this is your RAM. This maximum value is 1 volt. And this is happening at a time which is given by 1 upon 500 kilohertz. That comes out to be 2 microseconds. Okay, every 2 microseconds is there. Now, if you want 4 volt, so your duty should be how much? 4 upon 12. These are all ideal things. Because in the question, they have not given you what is your R on, RL, all those things they have not provided. So you should consider ideal case, right? So your duty should be 4 upon 12. So how much is this value?
1/3.
Okay. So it should be 1 by 3. So how much should be your Vcon?
Vcon by VRAMP is 1/3.
Yes. So your Vcon will be D into your VRAM, right? D into your maximum of your VRAM. So 1 by 3 into 1. So your Vcon will be 1 by 3 volt. Or that is 333.3 millivolt. Okay. So that is your Vcon. A very simple thing. Next, now suppose Vin becomes 4.8 volt. Vin has changed to 4.8 volts. So what happens is you say your Vin 2 is 4.8 volt. So what should be your D2 then? Your D2 will be 0.833. How? How will it be 0.833? Because your duty will be what? Your duty will be 4.8 divided by 12. So it is less than 0.5. So actually it is 48 upon 10 into 12. So it is 4 upon 10. So duty will be 0.4. Right?
Sir, V out or V in, which one is 4.8?
It's sorry, let me just see. Okay. Your V in is 4.8. V out is 4. No, sorry. V in is 4.8. V out is 4. Sorry. So it actually is 4 upon 4.8. Okay, so your D2 will be 0.833. So your Vcon will be D2 into VRAM, that is equal to 0.833 volt. So now your D2 would have shifted to say this value. This will be your Vcon 2. Okay, this is your Vcon 2. So it can adjust, like your Vcon can go from here to here, etc. It can adjust, your duty also can change. That's all fine. And that's all well and good. Right? But what they do in input voltage feed forward is, like, suppose this is your original one, where it is around 0.33. This is your Vcon 1. But now your input voltage has reduced. So when your input voltage has reduced, what is done is they make this ramp even more smaller. This ramp gets adjusted. So in your first case, your duty came out to be something like this, right? Came out to be something like this. So this was the duty which you required. But in the second case, your duty will come out to be something like this. So your duty has changed, your gate signal has changed, but your Vcon will remain the same. That is the beauty of input voltage feed forward. Your control voltage doesn't need to adjust so much because your ramp itself is adjusting accordingly. Okay, this is all bit idealistic, steady state values, everything. It will not exactly be the same. There will be some deviation, etc. All will be there. When there's a change, it will have some effect, everything. But this improves the performance. It kind of rejects the disturbances. And sir also showed by showing, he added a sine wave and he showed that a sine wave in the input voltage is having an effect in the output voltage. So that, and then also sir showed that when he added input voltage feed forward, how that rejects. There'll be a very, very small impact of that, but it can reject it very well. Okay, so that's the power of input voltage feed forward. And let us go to the question now. What is the architecture required for implementing input voltage feed forward? Okay, what is the architecture required? So now, what do you need? You need to generate this ramp. You have ramp generation. So can you tell me how do you generate this kind of waveform? You have to generate a ramp. What do you think is the way people use to generate a ramp? Any ideas? Any suggestions?
If we are using analog circuits, we can use op-amp for generating sawtooth generator. And in case of digital, we can use some microcontroller to generate a ramp.
Yeah. Okay. So in the case of op-amp, how will you generate actually?
In that inverting amplifier configuration, if we replace that feedback resistance by a transistor,
Okay.
and there parallel to that there will be a capacitor.
Okay.
So when the transistor is off, this it will be charging. Then when we suddenly on the transistor, that capacitor will quickly discharge through the transistor.
Oh, yes,
So,
exactly. Yeah. That's a nice way.
so that is. But I don't know whether there's any practical issue. This is a textbook image.
Yeah. There would be some slight issues that they'll have to design. The transistor should be able to withstand that large amount of current which will flow. It should have some resistance, etc. There will be some delay and all that will be there, but that's a good idea. So, like what actually even sir had told was that you will have a capacitor over here that will be connected to some current source, right? And then once it is reached the peak, you can turn on the switch, capacitor will discharge. Again, you open the switch and it will charge. So it will be like, it will be charging. Suppose this is your Q switch, right? Your switch is closed, it will open. Suddenly it will close for a short duration. It will bring back to zero. And then when the switch is again left open, it will again charge. So there will be some small portion where there will be this dead band. It will not be correct. There will be some small portion will be there. Okay, but there may be techniques and ways in which they can reduce the time. And these analog circuit designers, they have many ways. They come up with various circuits, and like it's like the trending field, like very large scale integration VLSI is like the trending field, booming field. They need all these designers, etc. Okay, so this slope is dependent on the current. So it is what? I current upon C. That's how far, that's the rate of change of the slope. So what they do is this I current is made proportional to your input voltage in the case of input voltage feed forward. So they can use various techniques such as current mirrors. They can use current mirrors, all those techniques they can use and they can generate it. Okay, those are stuff for analog signals. Okay, so that is how input voltage is done. Input voltage feed forward is done. So what now I want to stress upon is we have this buck converter. Okay, buck converter is there. Let me just draw how the inductor current looks like. This is how the inductor current looks like. Right? And this is my reference. Okay. This is my rising slope. This is my falling slope. In the case of buck converter, rising slope is V in minus V output by L, and falling slope is V output by L. Okay. So what happens is when input voltage will change, suppose your input voltage will increase, then what will happen? Can you tell me?
That slope will change.
Exactly. So that slope will change. No, it will be like this, something like that. Okay. So this slope will change. So I don't need to, have this current source and all this thing to multiply it proportional to input voltage, etc. The inductor current itself has that information of the slopes as the information of the input voltage having changed. So that enables, current mode control has that inherent information of the input voltage. So that is why current mode control, it is excellent in rejecting input voltage disturbance. That is the beauty of current mode control. That's one of the advantages. So, earlier we had this complicated circuit, do this, all that. But in current mode control, which is the actual inductor current which is there in your converter, that itself possesses the information. The input voltage has changed or output voltage has changed. All that information is there. So that's why current mode control is excellent in line rejecting input voltage disturbances. However, current mode control is slow for load current disturbances. It has an issue with that. So for that case, what do? We use load current feed forward. We use load current feed forward for current mode control. Okay. Okay. So yeah, that's what I wanted to say. Current mode control has inherent voltage input voltage feed forward action. It is there inbuilt inside it. Okay. So next we start with cascaded control. So can you tell me which of these are true? Which of these are false? We have many people here. We have Anushree, Arun is there, Divya is there, Suganya is there, Suresh is there. Okay. So please participate. Even if you give a wrong answer, your NPTEL grade will not go down. Your assignment grade also will not go down. There's no problem.
Option C is wrong. Usually POL converter is modeled as constant power load.
Yes, okay, okay.
Then option B is correct.
Okay.
Option A is also, I think, correct because POL is tightly regulated. IBC is nothing is mentioned regarding.
Okay.
That D is also correct.
D is also correct. So any one of you all has any objections to the answers or you're fine with it? Any of the others? Okay, you guys are submitting assignments, everything, right? For the course? Okay. Acha. So what is then question 4 is, we have a cascaded structure. Cascaded means one after another. So we have something known as an intermediate bus converter. They have then there's a large bus capacitor followed by a POL. There can be another POL, POL1, POL2, like that. Multiple POLs will be there, POL3, etc. And this is also coming from some other converter, some other input. Okay. So you want to control this. What happens is, this intermediate bus converters, sometimes it works in open loop also. You just give, like we have something known as the LLC converter or something, where, like in the case of buck converter, boost converter, what is done is we change the duty. We change the duty of the gate signal such that the voltage will change, etc. But if you run it in open loop, what do you mean? What do I mean by running in open loop is, you give some fixed duty, like you give 50% duty, your output voltage will be like half of your input voltage, approximately, something like that. That is what you mean by running open loop. Now, in the case of intermediate bus converter, also it runs in open loop, or it's slowly regulated. Slowly you regulate the output voltage. You don't regulate it very fast. But in the case of the POL converters, they are connected to your processor, okay, your LED, etc. Many things are there. So these require very, the voltage should not change much. You want 3.3 means you have to give 3.3. You want 1.8, you have to give 1.8. You cannot give 1.85, 1. This, etc. The current will change a lot. Input voltage will change. Still, you need to give. They are very sensitive equipment. You need to give regulated tight voltage. So to do that, these POLs, their feedback loop is made very fast. Their switching frequency is made very high, such that the size of the POLs is very low. So they are very fast. Their dynamics are much faster as compared to the IBC. So IBC is a very slow system. These POLs are very fast. So what happens is, when this IBC will see the POLs act as a load. They are acting as a load for the IBC converter. So the POLs can be modeled as a constant power source. There is a power which is being drawn by the POL at one particular instant is constant, and it can be modeled as a constant power source. Right? Even though fluctuations are there, this is there, still the POL in many literature it is modeled as a constant power source. Okay, so that's why these questions are there. IBC is typically lightly regulated. It is true. The POL converter has a buck type topology. Yes, we usually use step down converters, and it operates at a very high switching frequency to reduce the size of the converter. IBC converter can be modeled as a constant power load. No, it is the POL which is modeled as a constant power load. And the multivariable feedback approach can be used for designing the controllers for cascaded control. Is yes, this was taught in the lecture 18 about state feedback control, which Sir taught, where you use information of the POL converter to control the IBC, you use information of the IBC to control the POL. That also can be done. Okay. Any more queries and doubts regarding this, or can I proceed further? Okay. So I'll start with load current feed forward. Okay, so load current feed forward, can it be directly applied for converters operating in peak current mode control? Can the derivative of the output voltage be used as an estimator for load current in a buck converter? And input voltage feed forward is more essential than load current feed forward for converters operating in current mode control. So can you tell what are the answers for this? Any doubt you have, any points you want to raise, you can tell. The stage is yours.
Option B is correct.
Okay, good.
C is incorrect.
Okay, good, good. So B is correct, C is incorrect. Next.
A is not clear, sir. Please explain.
So question 5. In this we are dealing with load current feed forward. So what is load current feed forward? It is mostly used in current mode control. So what is done is you have a reference current, right? That is compared with your inductor current. That generates your reset. This your set pulse comes at a fixed frequency and you have your Q. Now, let us say like this is your reference current and this is your output voltage. This is how it is looking. Suddenly, and this is your load current. This is your load current is like this. Suddenly your load current will increase like this. So this is how your load current suddenly has changed. It happens. Let us say it goes from 10 ampere to 100 ampere. Suddenly it has increased. Like in your processor, etc. Suddenly if you connect, switch on many apps, or you suddenly start playing a game, okay, or you suddenly run MATLAB in your PC, laptop, suddenly it requires lots of power. To generate that power, you need to send lots of current. So lots of current is drawn. What happens in that case is when the load current suddenly increases, your output voltage will dip. It will dip, and due to regulation, it will come back. Okay, it will come back. So what will happen is this reference will slowly increase. So when it slowly increases, your current also will increase, and this is how your output voltage also will increase. So it is going to meet the load current demand as well as your output voltage will get regulated. That is how it works. Now, when you have feed forward control, what happens is, suppose your reference was like this. As feed forward is changed, your reference will immediately change. Because it realized it is detecting the directly proportional, it will change. When your reference changes, what will happen? Your current also will change directly, fast, and your output voltage also will have a smaller dip, slightly smaller, faster. So it is less dependent on load current. That is, your output voltage deviation is much, much smaller when you have load current feed forward. Okay, so this is the advantage. So all these things, when I talk, you will not directly understand. It will all come when you will simulate them. Okay, that's why, sir, as you have MATLAB access when you are enrolled in this course, sir has made many MATLAB models, sir has many MATLAB files, parameters, files, controller design files, all those files are there. He has taught also how to make all these blocks, etc. You should run those experiments. You should run those files, simulations. You should run it on your own. Then you'll be able to, appreciate all these things. Okay. Yeah. So what I was getting to was load current feed forward is there. So in the case of buck converter, your average inductor current is equal to your load current. So in that case, you can directly apply load current feed forward. Directly, the value of load current, you can directly add it to your reference, something like that. It will work. But in the case of a boost converter, your average load current is actually equal to I output upon 1 minus D. Okay. It is not directly proportional, but you just cannot add I output. So what is done in that case is the feed forward which they do, the feed forward which is implemented in the case of a boost will be I output into your V output by V in. Okay. Because your average IR is what? It is equal to I output upon 1 minus D, which is actually your I output into V output by V in. Okay, so there is, this is what is known as your, sorry, this is your scaling factor, which is required. This is your scaling factor, which is required. So that's why you just directly cannot apply load current. You just directly cannot add it. You have to scale it a bit. You have to scale it a bit. Okay. So any queries in this? So that's why, so current feed forward can be directly applied for converters operating peak current mode control. No, you have to have some scaling mechanism also should be there. So the derivative output voltage can be used as an estimator for load current in a buck converter. That is true. Because your derivative of the output voltage is actually like your capacitor current. And that capacitor current has information of your load current. So this is true. Input voltage feed forward is more essential than load current feed forward for converters operating on the current mode control. No. Because your current mode control has information of your input voltage, but it doesn't have information about your load current. That is why you need to uh, add load current feed forward for current mode control. You can add. It is better. Okay. So I'll proceed with the next question. It is this part. Okay, so can you guys provide me the answer? We have very talented people here. Many people are here. Please, one of you answer this question. Okay. Many of you are not answering. Achha. So one thing is this is like peak current mode control, which I've been telling. It is like peak current mode control. It is this is the architecture. So you'll require some IREF will be required. Let us say question 6. This is what current mode control. Your input voltage is 12 volt. Your output voltage is 20 volt. Your output power is 100 watt. Your switching frequency is 200 kilohertz. Your L is 3.3 microhenry. Okay. So now your output current is given by P out upon V out, right? So that is 100 upon 20. That is equal to 5 ampere. Okay. This is very simple, fast. Next, your average load current is actually equal to I out upon 1 minus D, which is equal to I out into V out upon V in, right? In an approximate sense, since we are considering they have not given any parasitic values, we are considering it. That is, I am not given any parasitic values. So this is actually your P out upon V in. That is 100 upon input voltage is 12. So what is 100 by 12?
8.33.
Okay, this is 8.333 ampere. Okay, this is your average current, IL average. Now, what do we need to do? So this is how your converter is operating. This is your reference current. So your reference current is IL average. This is your IL average, and this is your delta IL, right? So your reference IREF is equal to your IL average plus your delta IL by 2, right? Now your delta IL is what? This is your Vn upon L. This is the rising slope. So your delta IL is Vn upon L into this time. This time is your dt. So Vn upon L into dt. So Vn is 12 upon 3.3 into 10 to the power minus 6 into d is how much? D is 12 to 20. 12 to 20 would be like, let us say, less than, I think it's around 0.4. What is D? 1 minus V in upon V out. So it is 1 minus 12 upon 20. 1 minus 0.6. So it is 0.4. Okay, so D is 0.4. T is how much? 1 upon 200 kilohertz. So 1 upon 200 into 10 to the power 3. So can one calculate what is the delta IL?
$7.27.
Okay, so your delta IL comes out to be 7.27 ampere. Okay, are the others there? Others are not asking any questions, not answering. Please be more proactive. I ask you. So, your reference is then what? IL average plus delta IL by 2. Your IL average is what? 8.333 plus delta IL is, let us say, 7.27. 7.27 upon 2. So, how much does this become?
$11.97.
Okay, so approximately 12 ampere. Okay, this is the reference that you require. Okay. Similarly, load current feed forward is to be added. What modification is required? That is, we will add a signal which is I output into V output by Vn. That is which I have already shown over here. This logic. You will have to do this kind of logic. So what you will have is, you will have your reset set Q, right? This is generated from this comparator minus plus. This is your IREF dash. This is your IL. This is your set pulses which are coming over here. So this IREF dash will actually be equal to your IREF, which is coming from your controller, plus this is what? I output, the load feed forward, into your scaling factor, that is your V output by Vn. These together will be your load current, will be your current mode control with load current feed forward. So there will be this additional part will be there.
Sir, one doubt. In that feed forward term, is there any other factor like some scaling?
Scaling might be there if you have sensor gain, everything. See here, sensor gain, all that I'm not considering.
because I out into V out by V in is already IL.
Yes, exactly.
So we
So,
have
yes, you're very correct. Ideally, this is ideally, right? So your IREF dash is equal to I output into V output by V in, right? And then plus IREF. So this is already your IL average, right? So now your IREF, which you need to provide from your controller, should be just delta IL by 2. And that your controller will adjust because it has a controller. It will, PI or PID will be there, it will adjust. So Arun, are there any more queries?
no, sir, it is clear.
Okay. So this is like a combination of your feed forward and feedback. If you just use feed forward, you will not get the exact value. But you need this feedback which will adjust. Okay. Okay. So I'll proceed to the next question, that is voltage mode control. Okay. So here input is 12 volt, output is 40 volt, output power is 100 watt, switching frequency is 200 kilohertz, ramp slope is 0.1 volt per microsecond. Okay. So now how do we run this? Like, how do we do this? They're saying, this is what question? Question 7. So we have question 7. Input is again 12 volt. Output is 40 volt. Switching frequency is 200 kilohertz. And this ramp rate, this slope, this is 0.1 volt per microsecond. Okay. So this is going from some 0 to some maximum value, right? And this time t will be how much?
5 microsecond.
This time t will be 5 microsecond. So what will be this Vmax then?
0.1 into 5.
So it will be MC into t. So it will be 0.1 volt per microsecond into 5 microseconds. So microsecond gets cancelled. So it will become 0.5 volt. Okay. Any queries in this? Anusri, Divya, you all are being very quiet. Okay. Okay, so very good. So it is 0.5 volt. Next part. What is the required Vcon? So we need to generate some Vcon. We need to provide some sort of Vcon we need to give. This is the Vcon which we need. So you know your Vcon will be into D into your Vmax. Right? So as this is a boost converter, what is the D given by? D is equal to 1 minus V in upon V output. So that is 1 minus 12 upon 40. So what is this value?
0.7.
0.7. Okay. 0.7. So then what will be your Vcon then?
0.35.
0.35 volt. Okay. Yeah. So this is the way. Similarly, if you can add input voltage feed forward, all those things you can add, that you can check later. Input voltage feed forward doesn't work as well in a boost as compared to buck. There are certain non-linearities which come into the picture. Okay, so next we will go for the DC equivalent circuit point of view, which has not been taught to you guys, but I think this will be very useful for you all. So we will look into this. Okay. we are considering that this boost converter is operating in voltage mode control. And now we cannot use just apply V output is equal to V in upon 1 minus D, because we have been given this on resistance 10 milliohm, inductor DCR 5 milliohm. All these values have been given to us. These are like the parasitic resistance which are provided to us, right? So now, how do we quantify that if my on resistance is so much and my load changes, what is the impact? What is the required duty? Okay, so there is a method known as DC circuit averaging, which will be taught to you soon. But I just like to give you a brief exposure to this so that this idea can be there. Okay, and the thing with this course is you will not understand everything in one shot. See, I've been working on this, but whenever I go through these courses, this video, everything, I can understand better. I can understand things more. Right? There are things which I didn't understand, which I didn't realize, which I didn't consider, which I'm considering, which I'm understanding, which I'm learning, which I can incorporate everything, etc. So, as you learn this course and as I'm trying to do this problem solving and doubt clearing sessions, my objective is to just, give you some thoughts, give you some ideas, like just put some things within your mind. And slowly what will happen is those thoughts, those ideas, you will grasp it better and better. Learn it more well, more understand it well. You'll be able to relate this idea with that idea. You'll be able to interconnect. Because all these are interconnected. Voltage mode control, current mode control, not just completely different things. They are interconnected, right? They are basically there to control a converter. Similarly, what is the impact of this on resistance, this resistance, etc.? There various topics are there. Okay. So this has not been taught by sir, but I'm just putting it forward for you guys. Let's try to understand this. So we have this on resistance in the switches, 10 milliohm on resistance is there in the switches. We have the DCR of the inductor is 5 milliohm is there. Now when we have considered only these non-idealities, what will be the impact? What will be the output voltage be there? We want the output voltage to be 48 volt. So if we want this 48 volt, we need some duty. So how do we get that duty? Okay, let us check that. Okay. So question 8, this is DC equivalent circuit. So what you have in a boost converter, you have your Vin, you have your L, you have your RL, you have your R-on. This is your capacitor, and this is the load. Okay. This is your IC, and this is your I0, and this is your VL. Okay. And this is your inductor current. This is when your Q is 1. When your Q is 1, what happens is your VL is equal to Vin minus IL into RL plus R-on. And your IC is equal to minus V output by R load. This is when the case when Q is equal to 1. Let us consider case when Q is equal to 0. In that case, we have your Vin, right? We have your L. We have this RL. We further have this R-on. This part is open. We have this capacitor C. We have this load resistance. So this is the IL. This is your plus minus VL. This is your plus minus V output. Okay. This is the case when Q is equal to 0. That is your main switch is off. So now what do? We can write VL is Vin minus IL into RL plus R-on minus V output. Similarly, your capacitor current, which is this IC, that is equal to this inductor current minus the output current, that is equal to your IL minus your V output by R load. Any doubts in this? So what I have done, boost converter in okay, so the boost converter in CCM, it has only two modes, on, off. The equations in particular mode where I've incorporated the parasitics, I've considered that, I have written these equations. So now we want to do what is known as DC circuit averaging. In DC circuit averaging, what happens is the inductor will act as a short circuit. The capacitor will act as an open circuit. What do you mean by that? That means the average voltage across the inductor is 0. The average current to the capacitor is 0. If that is the case, okay, that is the case. In steady state, this is the case, okay? And this Q is equal to 1. This happens for the time t into t for my duty. Q equal to 0 occurs for the time 1 minus d into t. Okay. So now we know the average VL is 0. The average IC is 0. So that what is the average VL? That is 1 by t into what is my voltage when it is on? This is Vin minus IL into RL plus R on. Okay. That is Vn minus IL, RL minus IL into R on. This into dt plus this case. Vn minus IL into RL minus IL into R on minus V output into 1 minus d into t. Okay. So this average VL, which is 0. So 0 is equal to 1 by t. So, sorry. This t and this t and this t can get cancelled. So my 0 is equal to what? Vn minus IL into RL minus IL into R on into d plus Vn minus IL into RL minus IL into R on minus V output into 1 minus d. Right? So now, what can we say? We can say that Vn minus IL into RL minus IL into R on, if you take common, this will be d plus 1 minus d, right? Minus V output into 1 minus d. So that's why it becomes V output into 1 minus d is equal to Vn minus IL into RL minus IL into R on. That's why V output is equal to Vn minus IL RL minus IL into R on upon 1 minus d. Okay. Any queries in this? Okay. So similarly, my average IC is 0 for the capacitor. Average IC is 0. So that's why minus V output by R load into D plus IL minus V output upon R load into 1 minus D. These all are equal to 0. So 0 is equal to minus V output by R load into D plus 1 minus D plus IL into 1 minus D. That's why IL into 1 minus D is equal to V output upon R load. Okay. This is the expression. Okay. So now we know what is the V output, we know what is load, R load, but we don't know what is the average IL required, what is the average D required. Similarly, IL is unknown, D is unknown, because we know V output is given as what? V output is given as 48 volt. That is given to us. My output power is given as 100 watt. That means my R load, which is P output upon V output, that is 100 upon 48. What is this value of R load?
Sir, is it P equal to V square by R? Or
Correct. Sorry. Very right. What blunders I'm making. Okay. So R load is actually V square by P. V output square by P. 48 square by 100. So R load is how much?
23.04.
So 23.04 ohm. Okay. Very good. Now, we have this expression, but we don't know what is IL, we don't know what is D. We know what is V output. So it's a bit of a non-linear equation. What we can do is, we can write IL is equal to V output upon R load into 1 minus D, right? And this we substitute into this. So what do we get? We have V output into 1 minus D is equal to V in minus IL RL minus IL R on. So this is V in minus IL into RL plus R on. This is your V output into 1 minus D. So V output into 1 minus D is equal to V in minus V output upon R load into 1 minus D into RL plus R on. So you get V output into 1 minus D square is equal to V in into 1 minus D minus V output into RL plus R on. Sorry. Let us multiply throughout by R load into 1 minus D. What do we get? We get V output into 1 minus D square into R load. That is equal to V in into R load into 1 minus D minus V output into RL plus R on. Right? So now, what would be required is this expression should have to be solved. It would have to be solved. This nonlinear expression would have to be solved to compute D. And when you get this value of D, then you can generate your VCon. Any suggestions how to do that?
We can write V out by V in equal to in that format.
V out by V is equal to what?
Ideally, it should be 1 by 1 minus D if there are no parasitics.
No, but here
So
we are
it will be
necessarily considering the parasitics.
so it will be 1 by 1 minus D into some factors will be, if we take that term on the right side, V out, we can combine So V out by V in we can write.
Okay, no, you see over here, the thing is, we know what is V output. We know what is this, we know what is this, we know what is this, we know what is this. We know all this. We only don't know D. Achha, so what we can do instead is, we can write, we'll take all the terms to the right hand side, left hand side. So that is V output, 1 minus D square R load, minus V in R load, into 1 minus D, plus V output into RL plus R1. This is equal to 0. This is a quadratic expression. It looks a bit complicated. So what I'm thinking is, you would have learned it probably when you were doing your 9th, 10th, etc. When there's a bit of a complicated expression, we use the method of substitution. So let me substitute. Let 1 minus D is equal to X. So I have V output into R load into X squared minus V in into R load into X plus V output into RL plus R1. This is equal to 0. So when you will solve this, like this is like AX squared plus BX plus C is equal to 0. When you will solve this, you will get some value of X. These are the roots of the equation. And X is equal to 1 minus D. So X also will range of X should be between 0 to 1. So whichever solution, you will get two solutions of this equation. Whichever solution lies between 0 to 1, that is the required answer. And from that, you will get your D. Then you will get your D is equal to 1 minus X. And your VCon will be D into Vmax. So this is the process. Okay. Okay, this is like a very lengthy sum. Very, very lengthy sum. Let us see how many pages spent in this. Whoa. Started in the 9th page, 10th page, 11th page, 12th page, 13th page. Wow. Yeah, so this is a very complicated sum. Yes. Okay. So similarly, there's another sum which I made for controller design where they have a transfer function given by GP. And we have to design a PID controller which results in some closed loop poles so that we can have this frequency and this damping, etc. This is a bit of an advanced sum, but you could actually take a screenshot and you could try this on your own. Okay, if you have any doubts later, you can ask me. And many more of these controller design sums will come in your upcoming lectures. So now let's start some MATLAB demonstrations. Let us run it for voltage mode control. Let us check. This is a bit slow actually. Okay, so let me first give a recap then. Like what we considered in this session. So in this session, we considered what is known as a practical voltage source. Like we don't have any ideal battery. As you draw more current, the voltage of that terminal drops. That is because of these parasitic resistance, inductance, this capacitance and USR, etc. So all these things, they act as a disturbance. They act as a non-idealities. They are parasitics. So what will happen with all this is there'll be fluctuations. The output voltage will not be clean. Similarly, when we have our DC-DC converters, etc., what is desirable is we want our output voltage to be regulated like a flat, firm, constant value. But there will be load current disturbances, there will be fluctuations in the input voltage, etc. All these things will happen. In spite of all this, we want our control to work in such a way that it will give us a regulated fixed value. Okay. So to do that, we have also consider buck converter. We have many non-idealities are there, like this drop of the resistance, inductance, DCR, capacity, ESR, etc. And so like that, but we want to give a regulated output. So what do we do is we have a reference, we compare, we take the feedback of the output voltage that generates an error, which passes to the controller, which generates a duty that is sent to the converter, which further generates output voltage. So it is like a feedback. It's like a closed loop operation. If you have open loop means what? You don't take the feedback of the output voltage. You just give some reference value. It generates your duty and your converter will work. Okay, that is the way you run it. So this is a voltage mode control where there's a single loop. This is your loop. You compare your output voltage with the reference. The error which is generated passes to your controller that generates your VCon. That generates your reset and set signals. And that gives you a gate signal which goes to your converter which will run. So currently the simulation is running, MATLAB simulation, but it is very slow. Like this laptop is very slow. So it will be difficult, I think, to show it because it is running in the background. But let's hope it will work. Similarly, for current mode control, we have two loops. We have this fast inner current loop and we have this slow outer voltage loop. Okay, the advantage with current mode control is it kind of makes your inductor behave as like a constant current source. So it kind of takes the dynamics of the inductor to a very high frequency. So it results in the poles being separated and it becomes more robust, more easier to compensate the loop in the case of current mode control as compared to voltage mode control. Okay. But okay, voltage mode control is affected a lot, very susceptible to changes and fluctuations in the input voltage. So the audio susceptibility is poor in the case of voltage mode control. However, current mode control has that inherent input voltage information. But current mode control is affected a lot by the output load current. So for that, what is done is you use output voltage, output current feed forward. So input voltage feed forward is there, where this maximum value of the ramp is proportional to your input voltage. It gets adjusted accordingly. This is the ideal case. And then we give some scaling is there so that it becomes independent of input voltage. But all these are in the idealistic case. There will be some residue, some things left behind, some non-idealities, some unmodeled dynamics. To all that, to compensate for all that, what do? We run it. Feedback control is required. So this is question 3, where we consider input voltage feed forward. We showed how do we generate this ramp. Also we discussed we can use a constant current, like a current source, which magnitude can be adjusted in proportional to the input voltage. So that gives you input voltage feed forward. But how current mode control has that inherent input voltage feed forward it has. Then we discussed about cascaded control. We discussed about it. Then also we discussed about load current feed forward. What are the benefits of load current feed forward? What additional challenges is required? Like the scaling factor which is needed for load current feed forward. Similarly, we talked about current mode control. How do we generate that reference? The value of that reference is dependent on the average current plus the ripple current. So that's how the reference is generated. How do we calculate the ripple? Also is simple for a boost converter. It's very simple. Then what modification we have to do if we want to add this load current feed forward concept for current mode control. Then also we discussed about ramp. This ramp rate is there. So when this ramp rate is there, how do we realize what's the maximum value? Based on the maximum value, what is the duty which is required? Then next, then the final and last question which we did was the DC equivalent circuit, where we consider 2 different modes of the boost converter when it operates. Q1, Q0, where we analyze each of the equations. Then we average those equations. Since it is DC circuit averaging, is like the steady state. In steady state, the inductor works as a short circuit, capacitor works as an open circuit. So as inductor is a short circuit, the voltage, average voltage across the inductor is 0. And since the capacitor acts as an open circuit, the average current through the capacitor will be 0. So based on that, we took the average values we did. We found the expressions for output voltage. Similarly, the averaging the capacitor current, we got this expressions. So again, there are two unknowns. The duty is unknown and the inductor current value is unknown. So we substituted that in. So we got one expression which is given like this. So this is a non-linear expression. It is a second order expression which has to be solved, which can be solved when you put these values of V in R load, RL, R1 is given. And you can use in your calculator, scientific calculator, you will get the value. And you can get your D, and then you can get your VCOM. Okay? Okay, so this was what was done. Are there any doubts, any queries for today's class? Okay. Just 1 minute. Let me see why my MATLAB is not showing. Is it running? So this is the simulation. Okay. So if you can see over here, like the output voltage, we want it to be regulated at, let us say, around 24 volt. Like that is what I've said. So like this is how the steady state it works. Output voltage is around 24 volt. This is the inductor current. These are the gate signals. You can see when the gate signal is high, the inductor rises. When it is low, the inductor current falls. These small jumps are due to the ESR or the output capacitor, etc. So all these things you will you will finally understand it when you do the simulations. Further, if you will see what is my structure, you will see I have a reference value. From it I subtract the output voltage value. I get an error, I pass it to a PID controller. I have some scaling factor I have. Then I have a saturation block, which is required because I want my duty to be have some minimum and maximum values. So I've given 80% duty as my maximum, 20% as my minimum. That I compare with this repeating sequence. I have a repeating sequence is there, which is actually my RAM, which is rising, falling, rising, falling. And this is my set pulse, which generates my Q, the gate signal. So this is how voltage mode control is implemented. Okay. Okay, so I hope this session has been very useful to you guys. You can provide feedback. You can see the video will be uploaded on YouTube soon. And if you have any doubts, you can ask me also. You can comment and you can ask doubts as well. Okay, so thank you for joining.